So good morning, everyone. I'm Howie Callan from Airspace Services and ATO Mission Support. Welcome to our mornings of briefings from U.S. Airways on fleet performance characteristics. So the way this is going to work, we're going to run from 9 to about 10:30. We'll have an en route focus briefing, and then we'll do terminal from about 10:45 to noon. So this is going to be a full mornings here. So here to introduce our guest this morning is Chris Metz, Vice President of en route and Oceanic.
Good morning, everybody. Thanks for being here. And we recognize that we're in the new and improved Quesada Auditorium. Enjoy the new seats, the acoustics, and the video that you've got here. It's a great place to have meetings such as this. And we're very delighted this morning to welcome Captain Wes Googe to join us today, and he did so after having originally been scheduled, as many of you are aware, to have joined us around the week of the earthquake. And with the buildings closed and with us trying to inspect to see if the new auditorium could support the operation, we had to postpone it until today. We will be video casting this and preserving it such that it can be used at future times as well. And so keep that in mind as you come forward to either ask questions or as you observe the things that are being taught. We're very grateful to have Captain Googe with us. Let me tell you a little about him. He works with U.S. Airways and is based in Charlotte as a captain of the 737 and a check airman. And about a year and a half ago, he began what we'll call and what we're being happy to receive a part of, a grassroots effort to visit ATC facilities to help instruct and to educate the controller workforce on aircraft performance. As many of you are aware, we have not had the flight deck training program for many years, since 2001, so understanding the flight deck is of great importance to us in the en route environment as well as the terminal environment, and as we have come to find out, it's of great importance to our pilot colleagues. And so with that in mind, he took that grassroots effort, put together a program, which you'll be a part of today, and has been taking it to the field. He's already visited 8 of our en route facilities and 5 terminals. Last week, I believe, he was in Palmdale and spent some time with our colleagues at Los Angeles Center. He's also a prominent member, and you can ask for an autograph following the session if he's up for it. It may cost you just a little bit, but he is a member of our flight deck training video that is currently on the road, training our folks on the flight deck training program that's going on. He's also recently been involved with the optimization of airspace and procedures in the Metroplex, or the OAPM process, and will be representing U.S. Airways in the Charlotte design efforts. So with that in mind, please give a warm welcome and your attention to Captain Wes Googe. Thanks.
Thank you. Well, good morning, ladies and gentlemen. It's my pleasure to be here. Thanks to Howie Callan and Dennis Roberts and the rest of the good folks here in the FA. It'd be my pleasure for the next 2 to 3 hours to share some information with you. We bring greetings from, obviously, our senior leadership at U.S. Airways, from Doug Parker, Scott Kirby, and Robert Isom, down through Ed Billar, Senior Vice President of Flight Operations, Lyle Hogg, Vice President of Flight Operations, Bob Skinner, Director of Flight Training, and my boss, Steve Chinelli, Senior Check Airman. Chris is correct, that's what I do. I flew the line for quite a few years. I've been a check airman on and off with my first airline, Piedmont Airlines, and then with U.S. Airways. And through that time, I've developed, obviously, a good understanding and working relationship of how our aircraft do what they do in the NAS. And of course, it became apparent to us about a year and a half ago, and I'd say the industry's waking up to this, that we all tended to forget about the fact that 9/11 cut the door off and kept controllers out of our cockpit, because that was the one venue where we spent a lot of time sharing ideas. Controllers got to see the effect of their control instructions and what it did to us as crew members from a workload standpoint, what the airplane did, how it responded, what our tools were. So to that end, we sat down and brainstormed a little bit and thought, geez, there's really an opportunity here to start bringing this new workforce up, because we totally forgot how many people, or weren't really aware of how many people had been hired in the air traffic organization since 9/11, and it's a significant number. And many of those fine folks didn't have the benefit of an aviation background, either as an aviator or working in some aspect of aviation. So providing what we're going to talk about for the next little bit is hugely critical to giving them a database to be better at what they do. They have great skills, but providing that knowledge about individual aircraft specifics gives them a finer or a better way to do the expert controlling with the aircraft that we fly in the NAS today. So with that, we all know who I am. What I wanted to do is share a little video with you that I found on the internet. It's a little commercial that was run over in England, but I think it kind of highlighted what I saw about the difference between this and the AT.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you? Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
Is that not true? It's the old story, you don't know what you don't know. And that's where we are. A lot of people, not having the benefit to sit in the cockpit, don't know what's going on behind the scenes. So to that effect, that's why we're here today, to start bridging that gap, letting folks understand what we can do. So with the en route folks, this program started initially in Washington Center with the help of a young man named Tony Manzioni, who was in charge of the 5x5 program. We built a template for an en route program to share with them some key components about aircraft performance, about how the navigation boxes work, and probably more important, what we can do and what we can't do. Because we're not all the same. Although we all play with the same kind of airplanes in the NASA, we have varying capabilities depending on the amount of money we've been able to invest in our hardware and software material in the aircraft. So some of us are at varying levels. We're not all the same, and that's a key component for air traffic control. This is the Boeing fleet that we fly at U.S. Airways today. We actually are invested in Airbus, Boeing, and EMBRAER. These are the three model types that we fly. They're very similar to what the other airlines fly. The 737-3400 for us is not a long-term player as far as in the scheme of aircraft longevity. We've had these airplanes since 83 through since 1983, and they will be retired to be replaced by Airbus aircraft. The 75 equipment that we fly will continue in livery with us for probably the long term as well as the short term. We found that when we put wingless on this airplane, they're all ETOPS capable now. They do a really good job for us, primarily out of Phoenix into the Hawaiian market and back across the country, and then here on the East Coast we use them in a short-haul European mission to Shannon, Gatwick, some of the places they're on the coast of Europe, because they do a good job. They're very efficient. Probably the most efficient airplane we operate out of our combined fleet at this time. All these airplanes start from a navigation standpoint with a basic fundamental box in the belly of the airplane. The 7576 have three of them. It's an inertial reference system. And simply stated, at the core of this is a thing called a three-ring laser gyro. It shoots a laser beam inside a prism piece of glass, and that beam starts basically moving in a circular motion, and when it reaches a certain frequency, it is the equivalent of a mechanical spinning top, a gyroscope. Now this platform is stabilized. We put motion sensors on it to detect lateral and vertical motion, and we tell it where it is through lat-long input. Now the box knows where it is, it senses motion in 3 dimensions, and it drives the instrumentation in the cockpit as far as the attitude indicator, the HSI. Air data computers provide the input and the driving force behind the altimeter, vertical speed, airspeed, Mach number. All these things go through some type of mechanical technological device to send the data to the cockpit because so many other pieces of equipment use it. Unlike the old days of flying an airplane with a bellows-driven airspeed indicator, it came through a pitot tube and a static tube. We've all left that. Now, there are some instrumentation on the aircraft that still is very basic, a standby horizon and a standby altimeter and airspeed combination. Strictly used for a loss of all power on the airplane except the battery. Generally good for about 20 to 30 minutes. But it's very rare to non-existent we ever use this system. It's simply there as a safeguard in the event we were to have that happen. That's really the only instrumentation I look at on the airplane that harkens back to the days when I started to learn in the middle 70s. The aircraft also use the VOR DME system, at least Boeing does, on those that are non-GPS equipped, to do system correction because the boxes or the platforms will drift a little bit. But it'll take the 2 DME receivers and it uses paired channels that it has in a database, and when it finds 2 signals it can grab onto, it'll swing a DME arc, and when the 2 arcs cross, that's a known position. That's where the airplane is, and it will compare that to the IRS, and if the IRS is off a quarter of a mile or some such distance, it'll just true it up. It's an automatic process, runs in the background, much like your antiviral software in your computer. If the aircraft has GPS, we get the same effect, but using GPS, which is obviously even more accurate, which is what we're all driving toward. These are the speeds on the 7.5. It's just simply to show controllers some idea of what the speeds look like as far as maximum speeds. These are out of the pilot handbook, which very much reflects the Boeing pilot handbook. You'll see that theme carried through the other aircraft we fly, EMBRAER as well as Airbus. We do mention one thing, turbulent air penetration speed. Although it is a structural speed from the manufacturer, it's more importantly to me as a crew member, a passenger safety speed. Because when you look at the length of the fuselage of a 7.5, 7.6, any real airplane out there flying, and you start getting in a little bit of moderate chop, you get enough of a gyration, so to speak, in the back of the fuselage that if people are standing, you run the risk of causing them to fall. We worry about our flight attendants because they're out in the aisle pushing a cart up and down. You know, these carts are heavy. You start throwing them around, they'll hurt people. So although truly the number, that 290 knots up there would be used in a severe turbulence or greater event, we're pulling back to that speed to protect our passengers because we know even though the seatbelt sign's on, if they got to go, they're going to get up and go. And the flight attendants as well. So there's the speeds for the 7.6. They're very similar to the 7.5. It's a common type-rated airplane. Once we train a pilot to fly one, he flies both of them. It gives us a lot of flexibility in our schedule. We move people back and forth all the time. And that was a design feature when Boeing built both these airplanes. The 7.3 we operate today obviously is some of the oldest of this particular model type at Boeing. And I tell controllers, don't confuse us with a 787-900 series airplane because when Boeing moved to that greater air or enhanced airplane, from a design standpoint, the aerodynamicists changed the wing on it. The airfoil shape is different such that it allows this airplane, this 787-900 series airplane, to go to 41,000 feet and do Mach 8.0. My airplane won't do that. 3,400 at best is 37,000 feet, and on a good day with not a lot of weight, maybe Mach 7.7, maybe. You got to go low with this airplane to get the speeds that are listed in the pilot handbook, somewhere below 30,000 to achieve Mach 0.82. So it's not something we usually do. We don't flight plan the airplane that way. Normally the normal cruises you see there on the listing, about 7.4 to 7.5 is about what we do. And that, so it really is, realistically, in most of the airplanes we fly, that's probably the slowest one in the fleet that we fly at altitude. Here's the EMBRAER fleet, the 190. This is very similar to the 195, the 170, 175. So when I talk about this particular model, it really addresses the other 3 model types as well. built in Brazil in the rainforest. It is the newest airplane we possess on the property today. They're all 3 years or newer. I look at them from a construction standpoint. It's almost like a modular built airplane. The switchology in the cockpit now does something that's akin to what we see now in the modern technological world with computers. Everything's funneled through 2 modular avionic unit bays in the belly of the airplane, fore and aft, and computers decide how to turn things on. You turn a switch, but you just tell the computer, make this happen. And then it will decide the best way to do it, monitor the health, tell you when something's wrong, when it's broke. It also, in some cases, can downlink that information to our company maintenance people so that they have a good idea what's going on before we ever show up at the gate. And then, of course, the other thing is just like your new automobiles. Plug a laptop in it, do a diagnostic, and it'll tell you which box to replace. Plug and play. Unlike the old days of tracing wiring and other things to find where the problem is and then fixing the component. It has 2 IRSs in it, GPS for system correction, so it's a very accurate airplane. There are the speeds on the aircraft, so it's very comparable with anything else flying the NAS that the airline industry is using today. It's a very capable airplane from a range standpoint. Every day during the week, we depart 2 flights out of Philadelphia going to Cancun and Cozumel in this airplane, which most people consider to be a regional jet, but it's really not. And from a passenger standpoint, it's as comfortable to sit in as these seats you're sitting in this auditorium. So that's a nice airplane from our perspective. A lot of flexibility from a number of seats category, how we size to the market. And there's the Airbus fleet. Now, this is the mainstay of my company's future growth as far as aircraft fleet. We will be much like Southwest, and it will be a predominantly Airbus airline going forward, operating these 4 model types, and as a launch customer for the 350, that will be the one that will come on down the line as soon as Airbus finishes developing and building it. The 319, the 320, and the 321 are a common type-rated airplane. When I train you as a pilot to fly it, and you step on the flight deck, you will not be able to tell the difference between any of the 3 airplanes from a cockpit perspective because they're identical down to every switch. We did that on purpose, or Airbus did. Guys fly these airplanes interchangeably all day long, which gives us the flexibility of putting a different size fuselage into every market depending on seasonal passenger trends. Some places are heavy in the summer and light in the winter. So we always try to leave the gate with no empty seats, and if you travel, you know that. It's always a hard time finding an extra room to move around because there are no empty seats, and that's what we need. The 330 is a standalone airplane for us internationally. It's predominantly tasked with flying out of Philadelphia and Charlotte to all points in Europe. The longest mission it flies today is Philadelphia to Tel Aviv. It's a great airplane from a passenger standpoint. This and the 321s all have Wi-Fi systems in it, so you can surf the net as you're going across the country. Very comfortable environmental and seating. We really like these airplanes. We have discovered, though, there's one caveat, and the en route controllers tell us this all the time, because the one that they pin our ears down on is that 321. Because what we learned is when we fly this airplane in its predominant role, which is east-west coast transfer of people, and you load it up with gas and the weight and the cargo on a summer day, we find the airplane tends to be somewhat climb limited in that it doesn't perform very well. Now, this goes to the fact that all 3 of those model types share the same wing. So a 19, then a 20, and a 21 are all using the same physical size, the engines, all of it. So on heavyweight, hot days, this airplane struggles to get to altitude, and the controls will tell you about it real quick. They say, I think we got to move it out of the way because it just doesn't climb as good as everything else. That is true. But when you look at how Airbus designed this airplane, it was built initially for Europe. And long haul in Europe is really kind of short haul in the US, 800-900 miles. So they sized it more as a short haul, high density airplane. We wanted to go high density long haul. And so we struggle with it a little bit, but it's just something we've learned to live with, and with controllers' education and understanding, they know how to manage it in the NAS. And that's a good thing. They all have 3 IRSs in them, dual GPS for system correction, very accurate aircraft. There are the speeds on it. When you do get it to altitude, it will go fast. Another oddity for us as a crew member, the turbulent air penetration speed is a split number based on altitude. Below 20, it's one number. Above 20, it's another number. That theme carries through with all the Airbus family airplanes. at least in the 320 series or 319, 320 and higher. There's the 321, there's the 330. So let's now talk a little bit about aircraft performance as it goes to flight planning. Every day in Pittsburgh at our OCC Operational Control Center, there's probably between 40 and 50 dispatchers that are working, much like in a room that I consider the control room in an en route center. A little bit better, more lit, more outside light. And they sit down and use a set of systems, computer systems, to pull in all the necessary data they need to build a flight for today. Departure weather, destination weather, en route winds, temperature, pressures. They have a book of routings, company routes, as well as playbook routes, swap routes, all this stuff. And with their coordination with our ATC coordinators, they're able to put together the route that's going to work today that's the most efficient for the airplane. With access to the database for the performance of all these aircraft types, they can then plug in what ends up being the ultimate best altitude and the best routing for our trip today, say from Charlotte to LA. So when controllers look at their URIT tool and they see the flight plan, they look at the altitude, that's what we want to fly, because the airplane is fueled for that optimum mission. We don't, as a rule anymore, fuel airplanes on the probability of, well, we might on a remote day have to go 4,000 or 5,000 feet lower. We don't fuel it that way. We can't afford to anymore. Gas is too expensive, and you know that. When you go fill your car up, you know exactly what it feels like when they're raising a nickel or 10 cents. It hurts. So that's our biggest expense, and therefore we're very attentive to how much fuel we put on these airplanes. So to that end, we file obviously for the most optimized altitudes, and also we take into account if we know the rods are bad over certain parts of the country, we may file lower for a little bit and we'll adjust the fuel accordingly. This chart is out of the 757. It's actually replicated in the flight management computer, but what it does is it shows you a long-range cruise chart at Mach 80 for a 7.5. And the thing I really tell people to focus on is not so much the number, but the trend. The heavier the airplane, the lower that optimum altitude is going to be. And intuitively, it makes sense because you have to support more weight at altitude. You need a little bit more denser air, so the optimum altitude in that aerodynamic equation is going to work at some lower altitude. The lighter we get, the higher we're going to go. So for controllers for two identical aircraft in trail, you offer one altitude, and he jumps all over it, and the next person refuses it. He's probably heavier. Got a lot more people in there, which is a good thing for us. It means he's running a full load. We also consider a chart, which again is in the flight management computer, called the low and high speed buffet margin chart, or low speed, and some people call it a high speed stall chart. Now the low speed number that you see in the block Mach number and associated indicated is the stall speed. And I won't belabor that because most people understand the wing stalls and it doesn't have enough lift and the airplane noses over and we regain airspeed and recover. The high speed number, though, is a little different. From an aerodynamic standpoint, it's actually like the speed limit of the wing, because although the wing may actually go through Mach 1, the airframe and the wing together will not, because the aircraft are not designed for it. So, close to that Mach 821 number, you'll find that the wing develops a shock wave on top of it. And if you sit in the airplane going somewhere one day and you look and you happen to be in the overwing exit and look out over the wing on a sunny day, you'll see many times a shadow form. It starts at the root of the wing and it moves out toward the tip and toward the trailing edge. That is actually the shock wave. And as the air transits the shock wave, it speeds up and then slows down again, but it creates a pressure disturbance. And with it, it takes the center of lift of the wing. As that center of lift translates toward the trailing edge of the wing, it moves further away from the center of gravity. It exerts more of a moment, which is to be countered by the component of the tail, the downward lift. Ultimately, if it goes far enough, the wing wins the battle and the nose will start to pitch down, which further aggravates the issue because we're going to go faster. This is referred to as Mach tuck, which ultimately has disastrous results. Now, we have automation, bells, whistles, all these things on the airplane that tell us when we approach this speed. We also have another physical impression that we let crews have when they come to my airplane. We put them in the simulator, take them to altitude, and let them go as fast as they want to. As you approach this number, the whole airframe starts to shudder. It's a thing we want to imprint in the crews, because when you feel it, it's like what you understand when you get in a stall and the airplane shudders and then it starts to brake. We instinctively know what to do. We add power, we drop the nose, and we recover. With this, you feel the shudder, you instinctively know to pull the power back and slow down, and that solves it. So that's what the upper number means. And we see that as we come down in altitude, the gap between the low and the high speed number grow because we're in denser air. Where there is no number published, we don't go because the gap is so narrow, you can't fly it. And ultimately ends up in a single number called coffin corner, which we all remember. So that's what that chart's used for, and many times it dictates whether we go up or not. We also have an example of a fuel range chart here, but it's a penalty chart. What does it cost me as an airline if I can't get to my optimized altitude? In this case, we gave varying altitude losses, 2,000, 4,000, and 6,000 feet below the optimum. 6,000 feet, that last number is the additional burn, 15% additional burn. That's a lot of extra gas to have to burn. We didn't necessarily fuel the airplane for that. We were hoping, or we were planning on being at, say, 34,000 feet. Now we're pushed down to 28. If we have to stay there a significant period of time, especially on a cross-country mission, then what we'll do is we'll have to talk to dispatch through our ACARs, our little text box, and ask them to run the numbers again and say, do we have enough fuel? The obvious goal is to get back to altitude. That's the game. If we know that we're not going to be able to fly those altitudes going across the country, then obviously we won't file it for that altitude and we'll fuel it accordingly for that. Let's talk about en route descents. I give controllers a couple basic formula that I learned when I first came to this industry in 1984. Flying with a bunch of old captains, you know, because back then it was all done up here in our head. We didn't have the benefit of a flight management computer or an FMS. Simply stated, with an airplane, transport category airplane, it really works for most all the other jets as well, you pull the power back to idle thrust and let the airplane descend at a constant Mach number and then a constant airspeed. It usually loses 1,000 feet for every 3 miles you move forward. There you go, 3 for 1. So it's when you're sitting at altitude in the cockpit with me and you know we're going to Vegas or someplace, and at 35,000 feet, we're thinking at 105 miles from the airport, we need to be starting down. If we're not, we're asking that controller, what's up? Because anything beyond that runs the risk that we're end up having to either do a 360 or do some kind of off-course vector to get the airplane down. So there you go, that's how we think. We shade that distance for headwinds or tailwinds. If there's a severe headwind, 2.5 miles for every 1,000 foot of altitude loss, maybe 2 miles. 3.5 miles to 4 miles the other way. But that's how we've done it. The box mimics that, except it does it in a much more precise way because it knows exactly where it is and it can run that arithmetic calculation, 10 times a microsecond? That's why we have computers. So this is a page out of the FMC and the 737-400 that we fly at US Airways. It's a Smith's box. We set it up for a descent into Charlotte, and on the arrival, since our boxes possess in the database all the stars and SIDs for every airport we go into, they're all in the database with the altitude and or speed constraints. We don't have to do any of that work. It's already in there. Can we create it? Yes, we can. It's a manual input. It's very easy. We can build fixes, fixes around fixes. Anything with a DME, radial DME, or anything that you want, we can do lat long. It takes a little longer for the fingers to crunch the numbers in there, but we can do all that. And then put an altitude and or a speed constraint on that fix. But all these are populated in there, as is every fix in the NAS, every NRS waypoint in the NAS, every holding pattern, NDB, all of it. It's all there. So we pull it up, load it, and it says that when we get to a Dina intersection, we're going to be at 12,250 knots. The aircraft's going to want to descend initially at this target speed of Mach 746 and then transition to 311 knots. That number is derived from a thing that Boeing gave us called Tactical Cost Index. It is a measure of the operational cost of doing business with the airplane as opposed to the price of a gallon of Jet A. The corporation decides how that intermix or relationship will work, and they'll issue us a cost number. Generally at US Airways today for the 7.3, we use a tactical cost index of 45. That's what drives that number up there. Can I make it different? I certainly can. I can populate any number the controller wants, Mach number and or indicated speed. So that's what the airplane's going to do when it starts to descend is meet these numbers. It'll also look at any number constrained either altitude or speed-wise in the descent at any fix and meet it. In this case, the only one we see is the Adena constraint of 12,000 feet, 250 knots. So about 1,000 feet prior to level off in that descent to that fix, it's going to start shading the sink rate to let the speed roll back so that it'll be at 250 knots exactly at that fix. And it knows exactly how much to lead distance-wise on the turn to allow that to happen. It's a very accurate box. We also have a forecast page which allows me to put in there descent winds out of altitude as well as the altimeter change. So it fine-tunes that descent path down to feet. And as we fly the airplane, we can see our verticals. We see a vertical path deviation, which tells us whether we're above or below the path. So we've done all that, put it in the box, and when we're driving along, in this case at 28,000 feet, when that top of descent number, or T over D number, goes to 0, it's counting down, then because we're hooked up to the auto flight and auto thrust system, the thrust levers drive back to idle thrust, the nose pitches over, and we go down for a ride. And we sit there as crew members and watch it with the luxury of being totally involved with our situational environment, both outside the cockpit and inside, versus being only focused on flying the airplane. That's a good thing for me, because we have so many more balls to juggle, as they say now in aviation, than we used to 25 years ago. So it's a good system. It really works well for us. A lot of this has been around for 25 years. We also have a feature called the en route cruise descent. Just allows me to let the box use it to make small altitude changes coming across the country to keep me in the box from an automation standpoint. Simply descends the airplane to 1,000 feet a minute. If the controller wants more than that, expedited descent, then I have to go to the autopilot and use that, either a vertical speed or a level change maneuver, to get the airplane to come down quicker. Either one, I mean, it does what it does. It's a very good system. So we fly the airplane along, we made the descent, but today the controller says, you know, I really was gonna let you go to where you would normally start down, but I can't do that. I got crossing traffic, I need you to start down early. Oh, well, Boeing gave us another tool we've had for 25 years called the capture mode. Now, the good thing about capture, and it's now referred to as descend now, is when I execute it, the airplane will start down to 1,000 feet a minute until it captures the original descent profile at idle thrust, pulls the power back, and then it finishes the maneuver at idle thrust. Therefore, the controller got what they needed, an early descent, but I got what I would like, which is most of an efficient descent as much as possible. So let's talk about descent issues. What would confound the situation in the cockpit and maybe forget to either program or monitor what this airplane's doing? Well, first of all, we train our crews about the difference between cruise and path descents. It's a compatibility issue. You don't use a cruise descent with a star as a rule. It's a very simple thing, but it can be an issue if they made a mistake. Flight crew workload distractions. What interrupts my life and makes things challenging in the cockpit? Well, we've developed and contracted with a company now to take care of our medical issues. We don't diagnose sick people. I'm not good at it, and I don't have malpractice insurance, to be honest with you. It would be a deal breaker for me. But that's what we used to do. Flight attendants were trained in CPR. We did the best we could. Do we divert? Do we go on? How do you know you did the right thing? Now we hook up with a company in Phoenix called MedLink, and through a communications link through AirInc to dispatch and then a phone patch back to these doctors, they diagnose the issue. They tell us whether we need to divert immediately or we continue on to destination. Most controllers hear it as the fact that they talk about we need to deviate now or we're going to continue on with a medical problem, need to have someone meet us at the airport. At that point, we're in the execution phase of where we go with this person. What controllers are not aware of is during the MedLink process, at least for us at US Airways, there's a guy offline in the cockpit because he's dealing with this transfer of information between the back end of the airplane and this phone patch to Phoenix. Therefore, when they issue me a control instruction, I'm by myself. Right now, we're not really telling en route controllers that unless we just happen to think to mention it to them, because they understand the deal about when a person leaves to go to the bathroom, because they know a person's going to put a mask on above 24,000 feet. That's the FAR. So they hear the muffled talk in the mask, and they go, oh, somebody's left. So build a bubble around this guy. Give him a little extra room. Well, I want them to know that if I'm doing a MedLink discussion, during the discussion phase, give me an extra bubble. And it's something I'm working with our leadership at the company to include it as part of a notification in the MedLink checklist, okay? The other one is passenger disruptions. And we all, to some degree, understand that. That's humanistic, deals with personalities, it deals with people who maybe, I don't know, had a little bit extra to drink than they should have or came on that way. Or they looked at their ticket and go, my God, they charged me this much, and they compare it to the guy next to them who paid $50, and they get mad about it. I've seen that. So the problem for us is we've dealt with this in the past, and you kind of managed it, and you get down, you get customer service involved. But since 9/11, the paradigm's changed for me. Because distractions mean more than just someone's upset. You know, maybe we remember United 990 left here going to Guyana about 2 or 3 months ago, and 2 guys got in a fist fight over the guy leaning his seat back. What does that mean? I mean, the crew member's probably thinking, how stupid can they be? And then the next thing that goes through their mind is this. Okay, we're their friends. Who else is in the airplane? That's what I think about now. Because I realize distractions are like a wreck at a car race. Everybody looks there, and nobody looks. The guy behind them gets up and leaves. That's what they want. I understand that. So that's what I think about. I fly currently today with a lot of people who are in the Federal Flight Deck Officers Program. They're armed. We know. No one gets the cockpit anymore. Never. Because we know the ultimate end of that particular maneuver is disastrous for everybody, and we're not going to let it happen. We tell controls, when you come ride with us again on the new FTT program, don't be surprised when a guy has a 9mm Glock that he's going to holster. That's his job. He volunteered for it, but the cockpit gets defended because we can't let it be taken. So that's a change for us, but it does change how you view events in the back of the cabin versus the way it was before 9/11. So it can be a distraction. Let's talk about the Airbus descent. It's called a managed descent. Airbus took a little bit different tack. Of course, they have a nav display because it's a glass cockpit. You can actually see the top of the descent as what they refer to as a hockey stick. When the airplane drives up to it, the captain will reach up and take the knob he's used to select the lower altitude, and he'll push it in and start the managed descent. But if the finger doesn't push the button in, it doesn't come down. There is no auto capture. That is a potential tripping point for him. So therefore, in that last 10 miles on the run up to that top of the descent, you got to pay attention because it's not going to move on its own. It's just not. That's a difference in Airbus versus Boeing. Boeings are all auto capture, okay? Yeah, so he has the same distractions I do with the exception of that auto capture feature. And then we look at the 190. The EMBRAER, like I said, is probably the most technologically capable aircraft we fly as far as the neat stuff as far as navigation, because on this airplane, on the nav display, in the bottom half of the screen, you're looking at the vertical profile of how the airplane is going to fly that path descent. You can tell exactly whether it's above or below the path in feet and see it in real time while you look at the top half of the nav display and see the lateral track. Three-dimensional view. We don't have that on any other airplane we fly, at least today we don't, except this one. Same system that's in the G5, the Gulfstream 550 and 650. It's state of the art. This is where it's at. His issues for him, because of the size of the engines in the descent, comes to the fact that it doesn't generate enough bleed air heat at altitude coming through these thin cloud layers. It could ice up. So the engine controls know to ramp up a fuel control schedule to allow it to spool up in power, would therefore make sure the engine doesn't ice up. But when you do that, you destroy your sink rate. So they have to use a speed brake to keep the sink consistent because controller wants you to see you make your crossing restriction. So the controller, it's seamless. They see nothing. In the crew view, it's a workload issue with the speed brake up and down depending on where the ice is on or off. So let's talk about fleet descent issues, headwind, tailwind, descent speed, speed reductions. Oh, there's that 3-for-1 profile again, that green line. Again, that's how we think. And we shade it back for 3.5 for tailwind and 2.5 for headwind. Now, for me as a crew member, what has changed since I started out in the 727 back in 1984 is what the aerodynamicists did at Boeing and Airbus and all these other manufacturers. They made these wings more efficient. They took some of those drag things off, and the ones that remained, they shrunk them in size. Translation, they're less effective. I think of it like having four-wheel disc brakes on a car. You take it to the shop, they strip it all off and give you 2 drum brakes on the front with 2 wheels, and then tell you to go run a race. Your feet are on the brake all the time. It takes all that. So we get the effect by using those devices earlier and probably for longer durations of time to solve descent issues. Notably, the descent issue with a headwind, because as the headwind goes away, the airplane picks up ground speed, it starts to push out in front of the profile, and we have to drag it back down from the red back toward the green line. And the speed brake's the way we accomplish that because we're already at idle thrust. A little bit more work, but it's certainly manageable. The one that we really struggle with is the speed reduction in the descent, because now you're changing the energy state of the airplane while you're descending. Same issue. Now, can we solve it? In most cases we can, provided we know about it soon enough. If you wait till the bottom of this descent profile in the last 3,000 or 4,000 feet of descent to level off, chances are we're not going to be able to solve it. But we'll tell you, we have a code word. We just say altitude, airspeed, you pick it, because you only get one, you don't get both. And that's the way it works. Or you turn us out, give us a heading, spin us, whatever. But that's how that works. So with that, I'm gonna spin off here and do a little next gen stuff with you that we're sharing with controllers, which is a conceptual brief on the optimized profile descent project that we worked on with Albuquerque Center, Phoenix Approach, PBN office, the aerospace guys, and us, the guys operating the airplane. 2-year process, okay? Where we were last year was Eagle 3, which is a conventional star arrival that had really no vertical optimization. And the way the Boeings would fly is something like this, because it's always a idle thrust descent. So sometimes the airplane reaches the altitude before it gets to the constraint to define the altitude, so it levels off. Those level segments are not necessarily good for us as an operator. And it doesn't really make sense when you're coming downhill that you would level off. You just want to come one consistent path all the way to that last altitude. Now the Airbus, you'll learn something here, I hope, a little bit different, called a geometric profile. It says, match the vertical speed for the altitude drop between fixes. And it does that through the use of power. So as the airplane descends, it will add or take power away to accomplish this particular desired outcome. And so therefore, if you ride in the back of the airplane, you hear the power come up for a while, and then it maybe comes back, and then it goes up for a while, and it comes back. What I liken that to is when I used to ride with this uncle of mine, he drove with 1 foot on the brake and 1 foot on the accelerator. Whiplash. It would be much easier if we built the procedure so the airplane, like that green line, could stay at idle thrust the entire time. And that really is the goal. Give it a seamless path to descend. So as my friend Brian Townsend gives me this little cute graph here, that's him in the airplane. We want to design the star so that we can produce a flight idle or near flight idle profile. We borrowed a page out of the CDA manual for Eurocontrol over in ICAO. Again, let's get rid of the level off segments. Let's make the airplane do this. One nice descent, least possible thrust from the highest possible altitude. Area of noise benefit, environmental benefit too. You know, they tell me for every gallon of jet A we burn, it's 20 pounds of CO2 out the tailpipe. So if you lose a gallon of gas and you don't burn it, there's 20 pounds we don't put out there. Why are OPDs not much practice? Well, it's new conceptual design. Work through the issues of compression, phraseology, and coordination. That's why we had all the important players in the room, because you got to have all the experts. Airspace experts, controlling experts, airplane experts. When you get done with that, you come up with a good product. It ultimately ended up in what now is the Eagle 4 arrival, which is not much different than the Eagle 3 laterally. They moved a couple of waypoints a mile or here or there. And of course, it ends up up there in the upper right. It splits off to either an east arrival or a west arrival, the 2 runway transitions. But the beauty of this thing is in the vertical. Now, instead of having an altitude at a fix, an at or above or an at or below, we have a window of altitudes. We just tell the airplane, you can be no higher than this and no lower than this. Anywhere in between is fair game, because we've already protected it. Do what you need to do to be at idle thrust. That's perfect for the airplane, because that's what it wants to do. And we also fix speeds to all those downline fixes so that we mitigate compression by telling everybody, you got to play at the same speed in the descent. You don't have the option of doing whatever you want to do. That's how procedures can get airplanes, put it in the right path, vertically as well as laterally, to give it the optimized way to get to the runway. So when you take that concept and go back to that slide I showed 3 or 4 ago about descent planning, the bottom of these windows protect for that high ground speed descent into Phoenix and or the short side arrival, because that's right in front of you to the runway. As the airplane slows coming out of altitude, it's going to start to drift up toward the middle of the window. We've already protected it. We just let the guy do what he does. If there is a headwind, then the top of the window protects that, as well as the long side arrival going to the opposite direction for landing. So when you put them all together, we have in essence put a tube of airspace from top to bottom, let the airplane seek its best altitude in the descent at idle thrust, and we get the best product. And we actually get what we paid for when we bought these airplanes with this technological capability. Now, in today's world, we can fly these manually. I can fly the same kind of arrival without the box. I'm not as good as the box, but I can make it work. I've been doing it for years anyway. But the box is so precise that when you watch this thing now in the Phoenix in the cockpit from an Airbus, the power's back all the way down, and passengers notice that. They hear it, the power comes back, and it doesn't come up for like 10 minutes, 15 minutes. What's up with that? Until eventually you hear the guy turn on, you see him turn on the funnel, you feel it, gear throws out, and the power comes up, and we configure and land. That's the world we're moving towards. This is how Next Gen will help us. We've trained all this with our crews for 2 years, how to work the descend via phraseology, how to fly the airplane, how to manage it, being pulled off the arrival and put back on. We've been doing this. So as an industry, we're prepared to move forward. Now we have to create the airspace through procedural changes to allow us to do that, and that's what we're working on. So let's talk about en route holds. Fleet types will honor protected airspace for the holding pattern. Early notification helps with fuel speed adjustments for max hold times. Communication of realistic hold time helps me as far as fuel planning. We as crew members know we have to have an alternate when weather dictates, but we're not real crazy about it because alternates generally create us a logistical problem and a passenger problem. Nobody likes going to Harrisburg, Pennsylvania at 11 o'clock at night when they were going to Philadelphia because that usually ends up in a bad bus ride into Philadelphia. And when you wear a uniform, you are the target of all anger. Because we know everybody possesses a cell phone, right? And who are they calling? Mama or daddy at the house, and they're all saying, "Well, it looks great to me. I don't know why you can't get in." Oh, they just had it out for you, son. They just didn't want you to get to the airport. It's in airlines, they do it all the time. I hear it, I know. I've been shot. It's like Custer's Last Stand. You're in the middle and they're all shooting at you. So we try to get there by managing our fuel. As soon as we know we're going to hold, even if it's 60 miles ahead of us, we're slowing back. Get to our holding speed. Why? We employ a thing called linear holding. Drag your feet to the fix so that we've chewed up enough of that EFC that maybe we do 3 trips in the pattern and then we go on to where we go. That's the idea. Once one heads that way, the rest of us figure it out. We move right with them because we all have the same issue. Fleet accuracy. These airplanes with a DME update are usually good within 0.2 of a mile of a known position. If it's got GPS, it's 100 feet. That's important for future of R&P and SAR approaches and all these things that we're working on as an industry and the FAA. Let's talk about flyover versus flyby convention. Flyover is easy, it just bore sights the fix and hits it. The flyby is a little different. The box uses this known ground speed, ground track, and the angular bank the airplane can employ in the turn, and that's how it figures out when to start the turn. The faster you go, you got to lead a little bit so that you can just cross that, hit that fix with the wingtip and go out the new track. And then, of course, it has something to do with course track geometry as well. It looks something like this, barring a plate out of Charlotte. The CAFO's the flyover and the CATSI's the flyby. But now we learned something when we got involved in the Airbus program years ago. It's got this thing that it does above 10,000 feet with course changes of greater than 40 degrees as a rule. The Honeywell system, which is in the older model Airbuses, it has a relationship with the flight control computer. And once the airplane gets above 10,000 feet, Airbus decided for passenger comfort issues, their word, not mine, that it starts to shade the amount of bank the airplane can utilize in the turn, such that when you get to altitude in the mid-20s and higher, this airplane's only using 5.5 to 7 degrees of bank. That's a pretty shallow rate of turn. So what you end up with is you end up with something that looks like this. Good old Boeing hitting the fix, and the Airbus does this. Now, from a controller standpoint, that's a rude awakening if you're not prepared for it. And those in the room that have worked en route, they know. They're shaking their head going, "Yep, seen that one, got that T-shirt." We hope they don't. But the problem is it can't use enough bank to make the turn. Now, the newer model boxes put in these Airbuses made by Thales, British-made company. GE has the rights to build it here in the U.S. That's going to new installs. It doesn't do this. It does like the Boeing does. So there is a difference out here. Right now, U.S. Airways has equipped, as of my last conversation, the entire Airbus fleet to Thales. So we've kind of left this issue behind. I understand that Delta's done the same thing and United's somewhere in the middle as far as conversion. But we still have Spirit and JetBlue and USA 3000 and Virgin America and some of these other foreign carriers as well as UPS and FedEx that fight this issue. It's what the box does. And it's a certification issue because, as my understanding is, there is no standard when it comes to box manufacturers as how they have these airplanes make these turns. There's no standard, so they can do what they want to do. So when I ran this program up in Potomac back last fall, they sent me this little ditty after I left after about 2 weeks, and I thought I'd share it with you.
FedEx 1282 Heavy, proceed direct launch, join the Terps departure.
Direct launch, and then we'll resume the Terps departure, FedEx.
So here's FedEx off of Baltimore, Washington. He's just made a right turn. He's going to fly to this intersection originally Terps, then Wants, and then he goes down here to the left toward a fix called Jimmy. The controller gave him an obvious shortcut from here up to once and then make the turn, saving him maybe a half a mile, good thing, okay? But unfortunately, he was not prepared for what this FedEx was going to do. It just caught him off guard. What you can't see right now is a range ring for an Airbus coming off of Dulles that's going to fly a track on another SID that goes against this one as he climbs up toward JFK. The SIDs are procedurally separated, okay? So there's nothing wrong with the way the procedures were built. It just depends on what the airplane does. So when we fast forward this, you'll see what happens.
FedEx 1282 Heavy, turn right, heading of 310.
Right turn 310, FedEx 1282 Heavy.
And there's a United Airbus passing at 2 o'clock and, correction, 10 o'clock and 3 miles eastbound, leaving 15,000.
Yeah, FedEx 1282 Heavy, we got him in sight in the rain here, and we did get an RA.
FedEx 1282 Heavy, roger. You direct to once?
Yes, sir, we're direct once, but to make the turn to Jimmy, it's given us a lead turn so that we don't overshoot Jimmy.
FedEx 1282 Heavy, roger. You're about 8 miles. You started that turn about 10 miles from once there. Maintain 17,000 heading.
That's a lot, isn't it? That's at 14,000 feet, not at 26. So for us, it was an awareness issue. I can't change this thing. It's the way it was built, but I can at least tell controllers, heads up, be aware, okay? And there's been a lot of discussions in the facilities when we show this and we talk about it afterwards. We get good feedback and good Q&A stuff. TCAS, let's talk about TCAS. What I'm gonna do is show you something I borrowed from my friends at United in Denver. This is a 7.6 simulator. We're in the simulator at 19,000 feet doing 440 knots across the ground. The traffic that you see is that little yellow diamond that says plus 05. He's coming at me head on, the same ground speed. So we're 880 knots closure rate, okay? TCAS is traffic alert and collision avoidance system as we know it. It's two Mode S transponders talking to each other. Matter of fact, we talk to everybody in the NAS when we're usually within 30, 40 miles of the aircraft. We see all these targets and they're talking to each other and looking at trajectories, okay? TCAS is designed to keep us separated. It's usually done based on time, not distance. It's called delta tau, how close you get in time. So this guy's coming at me, and at some point he's going to start descent. Understand that TCAS can give me as a crew member up to 11 audio commands as well as visual commands on how to fly the vertical with this airplane. Okay? They're all hand-flown maneuvers because, quite frankly, I'm going to move a lot faster than a piece of automation. Skin in the game, so to speak. So we'll see this work its way through, and we'll see some things that may not make sense to you initially, but for purposes of demonstration, we kind of played around with the thread a little bit to show you the variability of the TCAS.
Traffic.
So now there's the TA thread advisory. You see it went to a circle and it says plus 05. The numbers are climbing down or descending down because the airplane's descending. You see the arrow that indicates the traffic's descending at least 550 feet a minute.
Descend.
Okay, so there's the TCAS RA. It's a red square. We've now moved the airplane down to about a 1,500. Oops.
Climb now. Climb now. Climb.
Now the TCAS is directing a climb from initial descent. And this little trapezoid tells me where to put the pitch of the airplane as I hand fly it. That looks pretty close.
Clear of conflict.
Okay. Now we did that on purpose for the demonstration. It's not two real airplanes. But what we did with the threat is we told the threat initially, start down enough just to trip the RA. And that's what we did electronically on the keyboard. That forced the crew and the sim to start the descent. Once we saw where he was headed with the descent, we told the threat, match it. Crew member sees the airplane, panics, disregards the TCAS and just says, oh my God, he's climbing, let me descend. So now he matches it, and now the trajectories say, okay, we're going to hit. So then the TCAS and the sim for the crew says, turn it around and go the other way. And that's what we did. We actually had the threat kind of chase him, just to show you the variability and how well this thing can move around. It won't get hit if you follow the commands, and if he did what he was supposed to do as a real threat, we would have passed harmlessly, which with a lot more than what you saw was about 380 feet, okay? But that's the way TCAS works. Crews put a lot of faith in this. We get constantly asked, when would you not follow it? It's so rare as it probably never happens, but there are certain circumstances where Part 91, see and avoid, can be applied. But the situations are so unique, you very rarely, if ever, see them, okay? So that's what TCAS looks like. By the way, 5 seconds lead time to turn everything off and move the airplane. Once I'm in a vertical maneuver, 2.5 seconds to change that vertical maneuver. That's what it gives me enough lead time to do that. And I'm not allowed to move in the lateral. The vertical is the only thing I can touch. And controllers know that. Don't waste your time talking to me about an altitude because I'm not listening to you. I'm all in this box at that point. Okay, so the first thing that gets asked is, well, if you could see the airplane, wouldn't you just move? And I said, well, seeing the airplane's half the battle. But I had a couple little videos up here to kind of make the point. This one's easy. That's a 7.6 at 370 head on with you, and you're at 38,000. But he's got a contrail. Okay, that helps. That helps a lot. Does every airplane contrail? No. And when you see the closure rate, he's only 1,000 feet below us. Gone. Good old RVSM. That's why we have it, right? So, when you look at that, you go, geez, I don't think you'd have much time to kind of figure out and read the tea leaves and then make the turn, right? And I go, nope. That's why TCAS RA works really well, because it's going to do something with us way before we get to that point of actually seeing the fuselage. But in most cases, this is what we see, or more importantly, what we don't see. Okay? Look up, look out the window. This is a glass ND on a CRJ. And what do you see? Cloud formations, buildups, haze, thin layer cirrus. I don't see an airplane. Where's the airplane? I know he's there. Keep looking. Oh, there's a glint. Oh, there he is. And as soon as you acquire him, go past the window frame. Oh, he's gone again. Like, how can you do that? So visual acquisition and maintaining that acquisition is tough, especially at en route altitudes. Lower it's a little easier. So again, all I can offer is, if we ignore this little piece of traffic right here, and just look at this VFR advisory right here, 800 feet above me, and we're working en route center, going someplace. Maybe he's at 11.5 and I'm at 10,000 feet or whatever. And the guy just decides to do an abrupt left turn right in front of me descending. The RA will go off, but it's just me and him. There hadn't been anybody on the radio for the last 15 minutes. Conceivably, you can turn the autopilot off and just make a right turn and go right behind him as he moves from right to left. And truthfully, I've done that before, almost 15 years ago, with a small light general aviation twin who did exactly that. So see and avoid does work. Problem is, if the traffic's behind the airplane, you can't see him. So it doesn't do any good. There's no rear view mirror in the airplane. So again, you trust the RA. And if it's later in the day when all the bug smashers come out, oh geez, how can you pick him out? He pick him out on the screen, but when you look out in the window, you see 4 airplanes, you go, okay, which one is it? Time's ticking away. I need an answer now. You can't do it. It's just not practical. So the RA, in most all cases, solves this vertical issue as far as separation for us. Here back readback issues, we still work with our crews and with the ATO because that's one of our biggest threats. How do I know? Well, we can listen to a couple of things we kind of tell on ourselves here. Let me stop this and run the volume back up here.
Cactus 1021, descend now to level 260, cross Olean 13,000 at 250 knots, tap altimeter at 3010.
3010 and down to 260 now, and Olean at 10,250 knots, Cactus 1021.
And Cactus 1021, it's down to 26 now, Olean at 13,000, 13,250 knots.
All right, Olean 13,250 knots, 26 this time, Cactus 1051, 1020.
Okay.
My favorite is this.
Cactus 1648, Jackson, climb and maintain full at 310.
Oh, not that's not it.
Continue climb to flight level 340, Cactus 1648.
Negative, Cactus 1648, level 310.
Sorry about that. 310, thanks for confirming. Cactus 1648, 310.
Not a problem, sir.
And that's what we want to do is confirm it.
Cactus 1675, Jackson, under climb and maintain full level 260.
Climb to flight level 270, normal speed.
No, sir. Cactus 1675, climb and maintain full level 260, 26,000. Leaving for level 2400 normal speed.
Climb to flight level 260 and out of, what was it? 24 normal speed, Cactus 1675.
We're all human. The average age on the east for our pilots is about 55, 56 years old. So, you know, hearing aids. You know, the wheelchairs, everybody always thought was for the passengers. Oh, no. So, with that being said, I learned this from a controller over in Washington, at ZDC, Brian Downs. What do those numbers mean? And when you ask crew members, generally they'll focus on the altitude word. And then I'll tell our crew members when I do recurrent training with them before going in the sim, I said, no, it's a heading. And they go, okay. And then they go, I said, it's a speed. And they always look at me and go, well, you didn't tell me what it was. And I go, ooh, there's a message. How many times do we read back clearances with numbers in them? We just read the number back. And the controller makes a natural assumption. Well, he meant altitude because that's what I gave him, but he didn't say that. Sometimes that's a perception that can get us in trouble because he's not privy to the discussion in the cockpit where the other person says, no, I heard it as a heading. Are you sure? Oh, yeah. I'm staking my life on it. It was a heading, Captain. And so, you know, you get into this discussion. Who wins the argument? The best way to resolve it is what we've done procedurally in our FOM or Flight Operations Manual. If someone's not sure, ask the controller to restate the clearance and everybody get on the same page. And then we don't have problems. That's the way it works. So for us now, it's not a wish list, a maybe, ask. It's a procedure. That's what we do. Weather avoidance, we know that NexRad is not as great a tool as the airborne radar we have because I can move the antenna up and down. They can't. Okay, so there are limitations. For us, weather avoidance most of the time is what you see out the window. This is a storm cell over Holston Mountain going into Charlotte from the north, and Indy Center gave me the option, left or right, young man, which way do you want to go? From your viewpoint, which way would you want to go? To the right, Howie's dinner point. Hey, sure, you go where it's clear. Oh, now you're an aviator. I go where it's clear. Because the difference to me, I got to go around the storm, and then I'm going to go to the southeast. I can fly 15 right. I can go left, but I'm going to go 40 left. Because I realize with that downwind component, all that wind blowing the top side of that stuff, you give it a bigger berth. So sometimes it's easier to take the upwind jog, not the downwind jog. You avoid all of it. And then go in behind the storm and proceed on. Oops, what is it doing here? See if I can get it to, well, I had another picture here. I was going to, well, let me just get out of it. I can pick the one I want. This one right here. As you get close to the storm, we were getting ready to start the turn. You see this cloud layer above the, to the right of the storm. It's cirrus clouds. It's mostly ice crystals above the freezing level is what it is. And when you fly through this stuff, the tendency it has is to charge the airplane from a static electricity standpoint. And it takes the receivers in the airplane in the tank. It breaks the squelch, puts a lot of white background noise in there, actuated with pops, squeals, whistles. If there's lightning moving between cells, it's very difficult to hear controllers speak when you're in this stuff. It's no different than getting in your car, find the AM side, which nobody listens to, but find a place with no station and just turn it up. That's what we hear. And it just stays constant until eventually you pop out of this stuff and the static electricity finally is able to be discharged, and it clears up immediately. It's also the same time when we'd be susceptible to St. Elmo's fire. We used to remember that, taking our finger and running that purple lines around the windscreen of the airplane. You used to think it was neat, but that's all part of it, okay? As far as returns go, when you look at weather on the screen, the green is light precip, the yellow is moderate, and the red is heavy. You generally look for those open areas to fly through doing weather avoidance if you don't have any visual outside clues like we just saw. Sometimes when you have widespread rain events where you have a low pressure area in here, you fly through the green and to some degree the yellow. It's not a terrible ride. Might be a little bit of a light chop. We still tend to avoid the red because even if a widespread rain event with no vertical development is just a lot of downpours, the heavy downpours still will give you a little bit of chop, so we'll avoid those. But it's just part of what we've done for 30 years. I mean, there's a guy in this country, Archie Trammell. He taught us how to use the weather radar expertly, how to read storms, how to know how to penetrate and get through them. That's what we spent years learning how to do and do it every day. So it's just not that big a deal to us. You get severe storms, all red and very little yellow or green, usually avoid those. because it's not moving anywhere, and with all that red, and you can't quite see it, there's some purple in here. That's a Doppler effect with these new radars. It shows shear in the storm, significant shear, kind of things that break things apart. This is a storm system where there's several cells. In case that the controller can't offer a left turn with the airplane, then we just take it here through the green and navigate between the two big pieces of the weather, and then pop out on the other side and proceed on. That's exactly how we do weather avoidance. It's how we navigate to get from one side of a line of weather to another side. Fleet request no early descents if possible, no cross-country directs, in sector okay. What does that mean? I tell the folks in LA last week, no Hail Mary pass from LA to Charlotte direct. We won't take it, because we've learned that there's so many factors that affect this airplane going across the country, most predominantly wind, that we can punish ourselves going Great Circle route, spend more time in the air and burn more gas, which is not what we want to do because of this effect here. That high-level jet stream starts dipping and diving around the country. Flight planning or dispatch will start altering these routes, much like sailing. Keep the nose out of the wind as much as possible to a certain degree, and when you can catch the tailwind, grab it, okay, to a certain point. Because, again, we've realized the relationship of extra miles flown at a higher ground speed, you can do that to a certain point where you'll still spend less time in the air than if you go on the Great Circle route. So as a rule, we like to use that. Utilizing the NRS waypoint system was created 5 years ago to accomplish that. That's why we put all those waypoints in the database. Currently 1,600 of these in the NAS today. That's what the website, the FAA tells me, 6,600 at some point. Don't know when that's going to happen, but that's the ultimate goal. We can take a case study of smoothing out a route. This is a LAX to Charlotte trip. The blue line is the conventional routing filed over VORs and jet routes. 2 NRS waypoints here and here smooth that whole route out and make it basically a Great Circle route. No wind, this particular idea. So we shaved 20 miles off that route. 20 miles doesn't sound like a lot when a 1,945-mile trip, but in our world, that's huge, because that's every day with every airplane that comes this way. And we're all doing it now. You talk to controllers and you ask who probably refuses the most any kind of directs, those long-haul directs. United. They arguably do one of the best jobs in flight planning. And we're working very quickly to get right behind them because we see the benefit to us as an operator. We have to do it. We don't have a choice. The other place we use this is sometimes when we can mimic what controllers are doing with this. This is a Vegas to San Fran trip. Using the conventional nav-aid system, we would normally have to go up here to Coaldale and then hang a left turn for the arrival into San Francisco. Controllers would cut us a shortcut up here into Oakland Air Center's airspace. And we thought, well, if we had a fix, we could get around these 2 MOAs up here and then just make the turn on our own. And that's what we did with that fix right there. Now we actually helped the controller. We took a transmission off the table for him because we're going the way he would have sent us anyway, as a rule of thumb. So in some ways, we can actually use these waypoints to assist in traffic management by trying to, again, mimic what the controller has given us as a daily routine into some of these places based on the constraints they work with. Let's talk a little bit about next gen. I added this piece for your briefing. I don't usually get this far in the weeds with the air traffic folks because trying to get to a baseline, but we've partnered with the FAA over the last several years. Most notably, our Airbus program is the platform we're using to do a lot of this development. Our 330s are being equipped and have been equipped with electronic flight bags. Not the iPad, but an electronic flight bag sits up on the windowsill on a mount. Okay, it houses all the things that are pertinent to the airplane: the nav database, the charts, the approach plates, the pilot handbook, the FOM, everything that we would normally carry in a flight kit paper-wise is in this particular device. But it also gives us some other tools when we couple that with ADS-B. We can actually use that device to display the inputs and the technology we can employ with ADS-B. Air-to-air, air-to-ground, ground-to-ground SAM, ground-to-air self-contained. This is what it looks like in a 320 that has the same type of EFB, because we have a percentage of our 320s as well that are equipped, mostly in the Northeast, running the New York shuttle up to Boston and back to DC. Okay. Cockpit display traffic information. Again, this is moving us toward the fact that now with the ADS-B feed in, we can see other traffic out there. That gives us some opportunities we've never had before, both in sequencing and spacing, where the crew now plays an interactive role with air traffic and how they can do that. okay? And coupling it obviously with the automation in the airplane, auto thrust and auto flight system. So we can look at something which has been experimented with out over the overwater tracks coming from Europe, the entrail procedures. The challenge is in the old way where you couldn't see anybody at non-radar, basically talking to ATC through AirInc. To make altitude changes, it took a lot because the spacing requirements were big, separation minimums. But now with this new system, be able to see these airplanes out here, you can reduce these separation standards to give us more flexibility in moving to different altitudes for efficiency, which again is what we're looking for. Utilizing and leveraging the technology to make us better at what we do with the equipment we have. Therefore, creating these so-called entrail procedures which enable the climbs and descents where current non-ADS-B separation standards will prevent desirable altitude changes. Benefit, good. This is where we want to go. This is the things we're looking to that the technology will give us. Also, you see it in the vertical view. You see there below the lateral view, you see your airplane and the other one's on the tracks above and below you. That's the future, guys. Merging and spacing, using the same tools. Merging of aircraft along a common arrival stream, okay, where airplanes can see the other airplane in front of it. We actually employ a technology we've been experimenting with called FIMS, Flight Deck Interval Management System. Same thing, lock an airplane behind another one, let the controller dictate this is how much time you need to remain behind this piece of traffic, and the second airplane will adjust the speed accordingly to maintain that time spacing behind that aircraft exactly. So merging and spacing, taking all these traffic, lining them up. All the tools that speak to the future, which you're working to develop and help us with. So before I get into questions, I'll leave you with a little thing that I say to every controller group, en route, terminal, whatever. The thing that I think we forget about sometimes is that the traveling public looks at us realistically much like they look at people who take care of very important needs for them, whether it's medicine, accounting, legal, the professionals. That's what we are. Professionals fly airplanes, professionals manage the traffic, build procedures, and regulate the airspace. It's an important aspect of what we do. I think sometimes we as a group forget that we are professionals. It's a job, you come in, you get your check, you do your thing, you go home. But you can't forget a lot of those people that I see every day, they walk on and they don't give a second thought about, could I be in harm's way today? Is something bad going on? They don't think that way. They think about other things, which is what I want them to think about. Going to the beach, getting a little drink with the flower in it, and having a great time, that kind of thing. I like that, you know, because that's happy. That means they'll come back and spend more money, and we can continue to survive another day and make payroll. But it is a profession. Controllers do a very important job. They can't forget it. I tell them to come to work and think about that. Be proud of what you've done and what you will do. You didn't get there because someone gave it to you. You didn't get here because they gave it to you. You earned the right to be here. Okay, just like I earned the right to fly this airplane. I touch on any given day maybe 500 to 600 people, their lives. I take them up, defy gravity, and I put them back down, and they go about their business. I look at controllers. I can look at Darren and say, how many people do you touch in a day working en route at Atlanta Center? 5,000, 8,000 on a busy day? And all those people never know that he took care of them, got them up, got them down with no consequences. That's what they pay their money for. We cannot forget that. So as a group, we have to, as we march forward with the next gen, work collaboratively. We all have our individual piece of the puzzle, the key. You have the airspace, the technology, some other technical issues that are the keys to make airspace good for these technically advanced airplanes to fly. I have the airplane experience. That's what I spent 28 years doing, was building that experience and learning the technology. Coming to work every day, trying to improve my profession by taking the time to do self-study, because I realize that, as my dad used to say, you're only as good as your last flight. Tomorrow you got to prove yourself all over again. That's what we do because we're professionals. So we have to work together collaboratively, and when we do that, we end up with products that are really good. That's what happens, and it's good for everybody. The environment, it's good for the passenger, it's good for me as an operator, it's good for you as a regulatory body in the government. So, with that being said, guys, I'll entertain any questions you have. Unless you need to leave, you're free to go at any time. And thank you. Oh, yes, sir. Go ahead.
Hi, my name is Bill Copeland. I'm a retired American Airlines 76 captain. And when I left in 2004, the only thing that the navigation could really do was fly along a track to a fix. I don't think there was anything in that could do an interval management in terms of seconds. And I noticed you're using a 330 for that. Does it have specific software, or is there an upgrade that's being done, or what?
Yes, it's a specific piece of equipment that the FAA has helped with funding in a joint project to put that device on the airplane with an ADS-B feed in and out. And of course, it's limited testing for us right now. It's not widespread. It's predominantly focused on the Philadelphia market for us, and we're using our international traffic coming in from Europe. And it's set up in coordination with Boston Center and then, of course, with New York Center and Philly Tracon. To work the aircraft in, they pick two. We use a thing called RTA, Required Time of Arrival, which has been in our boxes forever. Dispatch picks the two airplanes to do it with. They focus them in a time factor to get them to a certain fix over certain times to get them close. And then the en route centers actually link them up through ADS-B. And the test to see that the second aircraft in trail will lock that time in and stay exactly a minute and a half behind the lead aircraft. And to some point in Philly's airspace, they discontinued to go ahead and put them on the ground. But it's proving the technology that it can work and be useful. Yes, sir.
Yes, sir. Thank you for your briefing this morning. My name is Eldridge Frazier. I'm from the Aviation Weather Group, specifically the Weather Technology in the Cockpit program.
Correct.
And you made a comment about NICSRAD versus your aircraft.
Airborne radar, yeah.
Radar. Do you see a need or a use for weather situational awareness in the cockpit for the en route? And what weather would you think would be beneficial to you in the en route environment?
Well, first of all, the answer about can we get products and should we get products is yes. Okay, it all comes to how you get them to the cockpit. Now, ADS-B, TISB, FISB, as they say, this in and out stuff, that's going to help that because that allows us to bring things in the cockpit through the EFB that we don't have right now. What we have done over the last 30 years, as my counterpart out there knows, Archie Trammell taught a lot of people how to use radar management. When you learn how to run that tilt, scan different segments of the storms, because storms are like human beings in a way. They have different aspects at different altitudes from head to bottom or from head to toe. You learn how to read the storm. You learn for the best places to move around storms, the best areas when it comes to big lines of weather, how to find the soft spots and get through. Again, that's where we have the benefit that the controller doesn't have because they can't tilt an antenna with NICSRAD. They get a display that's refreshed every 60 seconds or 30 seconds, whatever it is, and sometimes they're deceived with what they see because they'll call weather to us and then we fly right over the top of it or through it, it looks like from their perspective, and they're like, well, what good is that? We just told him he flew right through it. What he didn't know is that the piece of weather he called out topped out around 26,000 feet, and this airplane's sitting up at 30. So naturally, he did fly over the top of it. Sometimes we don't communicate that very well to controllers. We don't tell them that. If you give a controller a vertical component of a weather system, they don't forget it, and they realize that if it's early afternoon and this is a growing system, well, what's at 26,000 will be at 34,000 in an hour and a half, maybe 2 hours. What we would like to see and is being worked on is the ability so that we both see the same product. We get some things from the ground we don't normally get right now through this electronic flight bag, and the controller get the same thing. So when I talk to Darren or I talk to Howie as a controller, we're seeing the same picture. And when he sees me want to go 30 right or 20 left or whatever, yeah, I see exactly where you're going. I see exactly why you're going there. But right now, we don't possess that synergy of the displays, okay? Because the reality of it is we're going to fly in weather. Don't get me wrong. We will fly in weather. As my friend of mine told me years ago, I'd look out the window and say, Captain, God, it looks really bad. He goes, yeah, that's great, son. We're going anyway. They paid their money. They want to get there. That's what we're going to do. So we go out there. We learned how to manage weather, how to get through it. What I want the controller now is to see what I see. And so he therefore has a view into my thinking process, how I make my decisions. He can help me because he knows where I'm going instead of saying, where's this guy going? I mean, left, right, I don't know. When the only tool I can give him right now is he can look at the URET tool and see what the upper level winds are. And if he knows if I go upwind, I might be a little bit closer to the system that I'm flying around versus if I go downwind. That's one tool I can give him today. But beyond that, without him seeing what I see, it'd take too long to describe it. So those tools are important, and I do think we're going to move forward and get them. I've heard that. Anybody else? Well, listen, I certainly appreciate you taking your busy time to come and sit and listen to this, and again, thank you from U.S. Airways.
All right. Hey, thanks a lot. We're going to take a break, let Wes get a cup of coffee. And at 10:45, we're going to crank up with a more terminally focused briefing. A lot of the same stuff you'll see, but there'll be a lot of new stuff. You'll see some simulator work with some go-arounds and things like that are very interesting. So if you want to come back at 10:45, those of y'all that are watching on the web, we'll be back at 10:45 Eastern. Thanks.
Yeah.